All right. And I think I remember the notes not matching up, so I should probably make a note to myself to actually fix that. Okay, so let me grab my book and we'll get started on some questions in 10.3 and get you guys going. Okay, I'll be right back. Did you guys miss me? All right, so what happened in the chat? Okay. So we're in 11.3, 357, 31, and 33. Yeah, what are you guys going to do on your Fridays when we don't have help sessions anymore? Sleep? Can just keep going all summer long. Okay, so we are in 10 or 11, 11, 3, 5, and 7. Okay, so find a normal probability. So a normal distribution has a mean of x and a standard deviation of sigma. I'm reading the directions out of the book. I'm on page 760. Find the indicated probability for a randomly selected x value from the distribution. So we did not do a problem like this. I agree. I have a feeling a joke's coming. But I would highly recommend using your bell curve, and I think it's in your book as well. I'm just looking what page it's on. Yeah, they have it on page 757. I think the one that I have printed out in the notes. Okay, so for example, the probability that x is less than or equal to the mean of x plus 1 standard deviation is how you read number 5. You got 9 with examples? Okay. So 9 is similar, 5 is similar to 9. So it looks crazy, I agree, because when you look at this, it's like, what are they talking about? Because they have all kinds of Greek letters, right? But it's actually not too bad. So for example, number 5 is, what is the probability that some number x is less than or equal to the mean of x plus 1 standard deviation? Okay. Yeah, sigma. This is standard deviation. This is the mean or the average. Okay. So it's kind of like just decoding. It is a lowercase sigma. It's kind of decoding what they're saying in problem 5 on this bell curve. So what we said, which actually isn't specifically marked on here, so hopefully you mark this down. In order to have a standardized bell curve, the average is always right in the middle. So the mean is always right at the 0, the 50% tile, right at the height of the bell curve. That's where most of your values should be, right around the mean. So I think that makes sense. And then the bell curve has our different standard deviations. So they're saying, what is the probability that x is less than or equal to the mean plus 1 standard deviation? Well, this is the mean, and this is plus 1 standard deviation from the mean. So we're talking about drawing a line right here. Okay. So what they want to know is, what is the probability that x is less than or equal to this? So we're talking about that x falls somewhere in this part of the curve. Well, thankfully, when someone created this chart, they marked what 1 standard deviation is. Yep. So actually you can just look here because they marked what 1 standard deviation is. So the probability that x is less than or equal to the mean plus 1 standard deviation is 84.1%. The answer is what, 0.16. Did I write it wrong? Uh-oh. Let me look. Yeah, for number 3, it's 0.16. For number 5 is 0.84. Yeah. So they are writing them in decimals versus percentage. Sorry. Yes. So 3 is the opposite. Well, 3 is a little bit different. 3 is, what is the probability x is less than or equal to the mean minus 1 standard deviation? So in number 3, they're talking about minus 1 standard deviation, right? And I just drew all over where I wanted to look. But yep, it's right here. Cool. So that should give you 3, 5, 7, and 9. Okay, so then you have 11 through 15, which I did not. Oh, 7, you're confused. Oh, okay, we can do 7. Let's start over with a new. Oh, there we go. That's much cleaner. Okay, number 7 says, what is the probability, basically, that x is greater than or equal to the mean minus 1 standard deviation and less than or equal to the mean plus 1 standard deviation? There is a whole lot going on there. I agree, Elijah. So there's a whole lot going on with number 7. It's going to take me a while to write it out, right? Probability, we've got x minus 1 standard deviation is, so first of all, we want to know, what is the probability that x is greater than the average minus 1 standard deviation? So we're saying that x is bigger than this, right? But x is also smaller than the average plus 1 standard deviation. So the average plus 1 deviation is right here. Okay, so what is the probability that x is basically in between those two values? Yep, so the answer would be the middle added up. So you would add 15 and 15, 30, and 19 and 19, and you would get the probability of that. I think it's 68%, something like that. Cool. Okay. So 11, 13, and 15, I did not do an example for. I agree. But I am happy to do that. So a normal distribution has a mean of 33 and a standard deviation of 4. Find the probability that a randomly selected x value from the distribution is in the given interval. Okay, so I will do number 13 because I think 11, you guys should be able to see some of that in the back of your book. Okay, so this one, they make it a little bit more tricky for you because they don't just straight give you they don't normalize everything for you right away. So what they're saying is that the mean is 15, says at least 29. Okay, so you want me to do 15? Okay, I will do 15. You kind of do them all the same way. All right, so it has a mean of 33. So what that means is that right here, my mean is 33. Okay, my standard deviation is 5. So practically what that means is that if this is 33 right here, right at the middle is 33, then positive 1 standard deviation right here is going to be 33 plus 5, right? Because it's plus 1 standard deviation. So that's going to be 38, right? And what's over here where we're minus 1 standard deviation? 33 minus 5 is 28. That makes sense? Because we're really just talking about how far from it, not necessarily multiplying. Okay, so number 15 says, what is the probability that a randomly selected x value from the distribution is in the given interval? So what is the probability that your number you pick is at least 29? So this one's a little bit tricky, right? Because we have minus 1 standard deviation is at 28. So 29 is like right next to it, right about here, right? And this isn't going to be perfect, but the probability that it's greater than this, right? So when we read this chart down here, this is talking about the probability to here. So I would say the probability that it's at least 29, I would guess, is around 17%. So that would leave the probability that it's greater than 29 at about 83%. What do you think, Elijah? Oh, you're figuring out 13 now? All right, try 13 and see if you got that one. So between 21 and 41. Yeah, so 13 says between 21 and 41. So we have to keep going out here on this curve, right? So 2 sigmas is, if I can get my paintbrush to work, 2 sigmas would be at 43, right? And down here, 28, 2 sigmas would be at 23. And then down here would be at 18. Okay, so what is the probability that it's between 21 and 41 is the question. So 21 is kind of in between this 18 and 23, right? So I would say it's almost at, I'm going to use orange for, this is number 13. I'm going to use orange for number 13. So I would say 21, it's not exactly, but it's about at negative 2.5 sigma, right? And then 41 is about at, it's about here, right? So you're going to have a really large percentage. So you can either add up all these guys in the middle, or you could add up the guys on the outside and then subtract it from 100. Yep, you want to add up all the middle because we're talking about everything in the middle here. Yeah, about 97%, which I think is the answer. Yeah, I don't know. I would say either they haven't done it yet or they're going to do it. So I think it was actually good to go over that because I didn't do the specific ones. Any other questions? $31. All right. Ew, this one grosses me out because it's got this fly. Okay, 31 biology. The illustration shows a housefly at several times its actual size and indicates the fly's wing length. A study found that the wing lengths of houseflies are normally distributed with a mean of about 4.6 millimeters and a standard deviation of about 0.4 millimeters. What is the probability that a randomly selected housefly has a wing length of less than 5 millimeters? Okay, so what they're telling you is that the mean is 4.6 millimeters. So first off, I know that's not what I know. I know that the mean is 4.6 millimeters. Okay. And the standard deviation is 0.4 millimeters. Decimal point there. Decimal point. There we go. All right. So that means that if I do one standard deviation above the average, that is actually 5 millimeters, right? Because if I can write an M, because 4.6 plus 0.4 is 5. Okay, so what is the probability that a randomly selected housefly has a wing length of less than 5 millimeters? So this one's actually pretty easy, right? Because I'm just at one standard deviation. And so they're saying, what is the probability it has less than 5 millimeters of a wing length? So the probability that it has less than that is 84.1%. So I just look at my chart because it's exactly one standard deviation. That makes sense? It's not too bad, right? I think it's one of those things that looks really complicated. Like, they're throwing out sigma and all kinds of stuff, and it looks like, what? But then when you see it, it's like, oh, I can do that. Yeah, 33 is a little different because we didn't actually talk about what a z-score is. But z-scores are actually really, really easy. Okay, so for example, and actually, I just read this. I'm sorry, I was a little distracted. It says, what is the probability that a randomly selected housefly has a wing length of at least 5 millimeters? So I was reading it as less than, but it's at least 5 millimeters. So it should actually be the flip side. Yeah, it should actually be 16%. Sorry. Just for completeness. If you actually read that one, you're like, what? Okay, so the z values, yeah. The z value actually seems kind of like crazy, but it's actually really easy. So if you see on my chart here, my chart that I might know, the chart that's here, the standard deviation is kind of the line that we've been working with, and that has a percentage underneath it, right? The z-score, can you notice anything about the z-score? Like this is +1 standard deviation has a z-score of 1, +2 standard deviation has a z-score of 2, -2 standard deviation has a z-score of -2. So we did not talk specifically about what the z-score is, but it's actually just this little formula, and it tells you how it normalizes your standard deviation. Okay, so in this one that's easy with the fly wings, right? The z-score is basically the number you're talking about minus the average, the mean, divided by the standard deviation. Again, one of those formulas that looks super complicated, but is not. So for what we were just talking about, we wanted to know what is the probability that it's greater than 5 millimeters minus the average, 4.6, if I can write right, over the standard deviation. So guess what? If I did the z-score for that, it's 1. And guess what we picked on this thing? We just added 4.6 plus 0.4 and got 5 millimeters and figured out that that's a z-score or standard deviation of 1. So if we go to 33, right? Let's get a new graph here. Boxes of cereal are filled by a machine. Tests of the machine's accuracy show that the amount of cereal in each box varies. The weights are normally distributed with a mean of 20 ounces and a standard deviation of 0.25 ounces. Okay. Find the z-scores for weights of 19.4 ounces and 20.4 ounces. Okay. So we can use the formula or we can use a chart. I think we'll actually use the chart since that way we can use it for B and C. And you can use the z-score too. That's actually another way to do it. I just chose not to teach it that way, but that's another possibility. So what they're saying, let's put what we know on here. Okay. So we know that the average is 20 ounces. Okay. Has a standard deviation of, no, green's not good over there, 0.25 ounces, right? So 1 standard deviation above will be 20.25, right? 2 standard deviations above would be 20.5. Yep. So they want to know what's the z-score for 20.4. So it's not quite to 2, but it's not quite to 1. So I would say, yeah, rounding. Yeah, I'd say it's about 1.6 for 20.4 ounces. Does that make sense? You don't want to round it too much, Elijah. Yeah, I'd say around 1.6. Okay. And so then on the opposite side, we're going to subtract, right? So it's going to be 19.75 ounces. And then at 2, it's going to be, if my pen works, that's going to be about 19.5 ounces. Come on, pen. And at 3, it's going to be about 19.25. Okay. So what is the Z value of 19.4 ounces? That one's a little closer to, it's kind of in between these two, right? But a little closer here. So I would say it's about negative 2.4, which is also the same as negative 2.4 standard deviations, right? Okay. So then what is the probability that a randomly selected cereal box weighs at most 19.4 ounces? That's bad luck. You get a cereal box that at most weighs 19.4 ounces, right? So we said 19.4 is right here. And I just kind of went over top of where I'm trying to look. So the probability that it weighs at most 19.4 ounces is there's only like a basically less than 1% chance that that's the most that it weighs. That makes sense? Okay. And so what is the probability that the randomly selected cereal box weighs between 19.4 and 20.4 ounces? So then we're just going back up here. So what is the probability basically that it's between 1 and 95? So that's about a 94% probability that it's between those two values. All right. What do you guys think? What does everybody else think? You ready to do your homework now? Oh, 0.000008 for B? We only have 2 zeros, 0.008. So that rounds up to about 1%. Right? We're close enough. All right, James said good. So you're following along. Gonna rock out the bell curve. Okay, so on Friday, right before you guys left, we talked about select and draw conclusions from samples. So we talked about different kinds of samples. I think you guys all kind of rocked this out, but just let's see, just pulling my notes out here. Okay, so I'm just looking at your homework here. So 3 and 5, you're just basically going to say what kind of sample is being taken. And I think that, I don't know, do you guys want me to read through these again, or are you guys able to look that up? You guys can probably handle looking that up, right? So we have completely random samples. That means that you're going to just pick randomly throughout the population, right? We have systematic random samples. So systematic means that I know I'm not going to say put everybody's name in the entire co-op in a bucket and pull their names out, but I'm also going to pick every 10th person. So that's random, right? I'm going to pick every 10th person that comes through the door. So that's still random. And then we have some bias samples. So a bias sample is when you have already introduced some bias before you even survey your group. So we talked about this. Like if you would, you know, ask people at co-op about, you know, a Christian issue, you probably would get a biased response because you're going to find that, you know, the population is higher Christian than other, you know, random samples. So that was very helpful, I'm sure, that I just said all that. No, I think you guys all got that. That was pretty easy, right? Are you guys still here? You're like, oh, she's still talking about stuff. Oh, you're just finishing up your homework. I see. I see how it goes. Okay, so there is one more part of 10. No, and now I want to say 10, Elijah. There is one more part of 11.4, which I will do in class on Monday. But what I'd like to spend like 10 minutes doing, hopefully, is actually talking about 10.5. Okay. Because it's called a best fit function, and we're going to use Desmos for that. So it's actually way easier to use Desmos on the help session than in real life here. So what do I mean by best fit? So in the real world, we don't have a math book that gives you nice data that always just kind of fits into the perfect box of you know, oh, when X is 1, Y is this, and when X is 3, Y is this. In the real world, you're going to collect a bunch of data and then you're going to try to analyze it. And so we have to be able to come up with ways to predict what's going to happen. So one of the things that we use is called a best fit model. Oh yeah, so I wrote it right there. In the real world, math problems don't always come with everything laid out. So mathematicians and scientists have to model the data they've collected. And so we do this by plotting the data and then choosing the type of function that would best fit for this data. So what we're going to do is we're going to use Desmos for this. But before we even get started, I just want to do a quick review. So you see this little chart here. These are some of the most common equations that we use, types of function equations that we use to fit our data. So we could have a linear equation. So that means that we have a line that fits our data really well, and that would be awesome, right? You can have a quadratic. So if you plot your data, right, and your data looks like a line, then you're going to try to fit it to a line. If you plot your data and you get a nice parabola, then you think, oh, probably a quadratic, or part of a parabola, quadratic would work well. We have cubic functions, exponential functions, power functions. So we're going to look at all these different ways that we can model our data the best. And the reason data modeling is important is because we can use it to predict future data. So let's switch to Desmos. Give me 1 second here. Pause my screen. Switch over to Desmos. Hopefully you guys are all still awake. I know the bell curve was, you know, thrilling. Sorry. What are we doing now? Are you back? We're opening up Desmos. We are in 11.5. We did not finish 11.4. We'll do that on Monday. I just wanted to show you a little bit of 11.5 because it's Desmos. So what we're doing is called we're making the best fit to model data. Should we do 11.5 before Monday? Well, there's only 4 problems in 11.5, so if you choose to, you should just go ahead and go for it. If you don't have time, that's okay. Hey Greta, no problem. We just finished up 11.3, so I'm recording it if you need to go back. Okay, so what we're going to do is we're going to talk about what if we have a bunch of data? How do we model that data to actually make it useful? So I'm actually going to skip to problem number 3 on your notes, okay? This is speed versus efficiency. A study compared the car speed, X, and the average fuel efficiency, Y, in a certain car model. Let's make it exciting, right? So when a car is going 15 miles per hour, it's getting fuel efficiency of 22.3 miles per gallon, right? When it's going 50 miles per hour, it's actually getting a better fuel efficiency, 30.2 miles per hour. So what we want to do is we want to figure out what model fits this data, and then we're going to use it to predict some other fuel efficiencies. And it's not going to be perfect, but we should be able to do it pretty closely, right? So how do I do this you could do this by hand, but that would be a lot of work. So how do I do this in Desmos? Well, what you actually need to do is window pane your things. And what we're going to do is we're going to take this table of data and we're going to create a table in Desmos. And you can do this on your app too. So Elijah, I don't know exactly what we're doing on Monday, Elijah. We'll definitely finish up 11 on Monday and probably get into 12. And we might finish up 12 and then we'll be done with all of your algebra too. All right, but right now we gotta get through 11.5. So you get really exciting. You get to watch me create a table of data, all right? And I think it's not like Excel. I think you can actually create this in Excel and then import it over. Oh, look at that. It's predicting. That's so nice of you, Desmos. It predicted that I was going to keep counting by 5s. All right, so this is where it gets a little more tricky. I have to put in my fuel data, right? So X is in my miles per gallon of my car, and this is my fuel efficiency. Any of you guys care about fuel efficiency? Does anyone have do like super fuel efficiency, or their parents do that? There's like people that try to get their cars to be as efficient as possible and do things like turn off the car when they're at red lights and post. Some of you aren't driving yet, so that doesn't really count, right? Yeah. So if you buy is a Dart electric or is it a hybrid? Well, there's some people that like try to get their fuel efficiency as high as possible, so. All right, I'll check out Mythbusters. I don't actually do that for my car, so I don't know, but my husband had a friend that was like super into it. He was gonna try to, get awesome fuel efficiency. Okay, so now I put this table in and you're like, well, it didn't even graph it in Desmos. And that's because if you look at the X values, they're between 15 and 65, and the Y values are in the 20s and 30s. So we have to do a little work to make my X values look like, so I want to go between like 0 and 80, right? And my Y values we'll go from 0 to 40. There we go. All right, so here we go. Here is my graph of my data of fuel efficiency. Okay. So what I want to be able to do is to model this data the best way that I can. And I think actually Desmos has a plugin for this, so I need to find it and send it out afterwards. But what this is called is doing a regression model. So if you hear the word regression and you're like, I don't know how to do that, you actually do know how to do that. And what you're going to do is you're going to try to figure out what best models this data. So do you think a linear model is going to be best for this data? Does this look like a line? The answer is no, people. Does not look like a line. It's got a curve going on, right? I'm thinking more parabola-ish, right? Maybe even a cubic, I don't know. So how do we actually best fit our data? So this is the trickiest part, is figuring out how to use best fit in Desmos. So what you do is you have to say, I'm trying to fit y sub 1 and x sub 1. So those are my two variables. Yes, a table is a tool under here. So you can add a table. Okay, so you're going to say y sub 1, and I forget how to do it on here. Y, there's the sub button. There's probably a different way. Y sub 1, okay. It tells you this is a list. Now, instead of equals, what you want to use is this little squiggly. Because what the squiggly does is it approximates your data, and it's trying to do a best fit. If I said y sub 1 equals, it's going to try to come up with an exact, like this value equals this value, but we don't have that. So let's start with our simplest equation. What's the equation of a line? Y equals mx plus b. Yeah? Is that what that's called, Elijah? How do you say that? I wish I wish I had a mic, because I'm not even gonna. Tilde? I think that's right, actually, tilde. I've heard that before. Okay, so what this says is I want you, Desmos, to approximate a line, right? We said a line. We gave it a line, right? The line is mx plus b. Approximate the best fit line that meets my data and uses my table of x sub 1 and y sub 1. This is a terrible fit, right? Awful. It doesn't look anything like it. We also know that if you look at this box underneath here, what does this tell you? It tells you that for this particular purple line that Desmos gave you, that m is 0.09 and the b is 24.42. So it tells you what the equation is. And it also gives you this thing called an R value. I don't know if we specifically talked about R values in this class or not, but an R value, no, actually we did. I remember talking about it a long, long time ago. Bring it out of your brain somewhere. So an R value can be anywhere from 0 to 1, and the higher the R value, the better the correlation. And actually it can go to -1 if your graph's going the other way. But basically, the higher the number, the better you can get. Yes, I would say, James, I remember like talking to you about this, right? So like 0.5 is like not very good at all. So we're only at an R value of 0.628, something like that, right? Not a very good fit. So let's, instead of trying to model this after a linear equation, let's try a quadratic equation. So a quadratic would be ax squared, right, plus bx sub 1 plus c. Okay, so this is the equation of a quadratic, right? Ax squared plus bx plus 1 Well, you got to try. You got to try different ones, Elijah. You don't know. That's the whole point of it. You're trying to find the best model for your data, right? Well, I would say that this is a way better fit than the linear equation, right? It actually follows the curve of the data. This one actually doesn't give me an R value, but it gives me the R squared value, which is 9.96. So that means I have a pretty good model going on, right? So what you're going to need to do when you do this section, this is what I would recommend actually. Actually, before I even make a recommendation, I'm pretty sure there's a Desmos regression site. So Desmos has already pre-plugged in all the different regression models, and you just have to put the table in. So that will be the first thing. Look for an email with that in it. If not, what you're trying to do is you're trying to model some different equations to see which one fits best. Okay. And the reason that we do that is if you're a scientist or a mathematician using real data and you want to predict what's going to happen, then hopefully you should be able to do so. So, for example, our table only goes up to 65 miles per hour. So what would I predict my fuel efficiency would be at 70 miles per hour? I would predict, if I can get my cursor there, that my fuel efficiency would go down at 70 miles per hour. So I would predict it would be about 25.7 miles per gallon. No. Yep. Yes, miles per gallon at 70 miles per hour. Now, is this a perfect, the faster you go, yep. Is this a perfect model? No, because if I'm at 0 miles per hour, there's no way that I'm getting 13.7 miles per gallon. Right? Yeah. So we have to have some parameters. Within my curve here, right, between 15 and 65, I probably have a pretty good prediction. So if I wanted you to predict what is the miles per gallon that I'm going to get at 53, okay? So if I go to 53, I'm going to have a pretty good prediction that I'm going to get about 30 miles per gallon. But when I go out here and I say, okay, what's my miles per gallon at, let's say I have a really, whoa, my computer just darkened. I have a really fast car and I am somewhere on the Autobahn. Yeah, I would not recommend trying this. But let's say that my car is going 100 miles per hour. I think I'm probably going to get better than 7 miles per gallon. Yeah. Yeah. If you're really pushing it and you're over 110 miles per gallon, you're just getting, it's giving back to you. So you can see that best fit models is a way to model our data to make some predictions, but they're not perfect. All right, so we will talk more about 11.4 and 11.5 on Monday. So you'll definitely want to have your calculator with you to go over 11.5, unless you want to graph this all out by hand, which does not sound fun to me. So yeah, the table explains city and highway. Yep. So when you have go to buy a car and it's got the city miles and the highway miles. All right, good deal. Thanks, guys, for hanging with me. Like I said, I'll look and see if I'm almost positive, I'm almost 100% positive there is a regression kind of tool for Desmos that I've used in the past. I just have to find it. So I'll send that to you and we'll go over some more of these on Monday. So I think it's actually interesting. It's pretty cool that you can have real data that you can actually predict versus just, some math teacher made up data. Technically, this was made up by a math teacher. Maybe we can come up with our own data on Monday about something and model it. Wouldn't that be fun? All right, good deal. You guys have a good day. We're done 2 minutes early. Isn't that awesome? All right, see you guys. Have a good day. Bye, Mackenzie. Bye, Greta. Thanks, guys.